Good evening, boys and girls. Welcome to another lesson on Physical Sciences Grade 12, brought to you by Africa Teen Geeks and the Department of Basic Education. And we are having our physics rewrite lessons. And this is because we are going to rewrite Physical Sciences Paper 2 on the 17th of November, and we want to make sure that you are well prepared once more. So have all the courage and join me in this particular lesson, and I hope that you are going to enjoy it. Now, in this lesson, my dear learners, we are going to focus on physical properties. We are still looking into organic chemistry, but for today, we are definitely going to focus on physical properties. And this is because we are continuing with this section, which is quite long because it has 3 parts, which is nomenclature, physical properties, as well as organic reactions. But for today, we are definitely just going to look at physical properties. So you know that the examination guideline is definitely going to guide you in terms of what you need to know on this section on nomenclature. And then we will be learning these physical properties, and we'll do that using questions from November 2019 National Examination Paper for Physical Sciences Paper 2, and that is going to enhance our knowledge and grow it much better in terms of physical properties. And lastly, I will be giving you more tips as to how you need to prepare for this particular upcoming examination. Are we together? Right, so let us go straight into it and look at the questions. Right, this is a question on physical properties. It is most likely going to be question 3. And this question, I have sourced it from November 2019 national paper, and it is on physical properties. Now, let us look at the question that has been presented to us here. It reads as follows. The boiling point of 5 organic compounds P, Q, R, S, and T are studied. And then they give us a table there and they give us the compounds P, Q, R, S, and T. And we can see that the IUPAC name has also been given. And the IUPAC name there is pentanal. So I can see that the name ends with AL. Immediately when the name ends with AL, I can definitely identify that it belongs to the homologous series aldehydes. Then Q, it's 2,2 dimethyl butane. So the name ends with ANE, and there it's dimethyl, so it's carbons and hydrogens only. So if it ends with ANE there and it's a hydrocarbon, definitely I know this molecule is an alkane. Right? Then I go to molecule R, it's 3-methyl pentane, it ends with ANE, it's methyl, it's pentane, so it's a hydrocarbon, so it's definitely an alkane. When I look at molecule S, which is hexane, the name ends with ANE. It is a hydrocarbon because it contains only carbon and hydrogen atoms. Then I definitely know that this molecule is also an alkane. Then the other molecule is pentan-1-ol. So I can see that the name ends with OL. So this molecule definitely belongs to the homologous series alcohols. So here I am looking at organic molecules. Some of them are from the same homologous series, which is Q, R, and S, and they are different from P and T, which are from different homologous series. Now, we are given question 3.1 and we are required to define the term boiling point. Firstly, my dear learners, I need to remind you that when you give a definition, we are only going to accept the definitions that are in your examination guidelines. And hence, I have indicated to you yesterday that you must be having examination guidelines. You can't go into the examination without an examination guideline. So you definitely need that, my dear learners, because that's where you are going to get the correct definition. Furthermore, as I have indicated to you as well before, I said when we give you a question and it's on physical properties, we will definitely ask you to define at least one or two of these physical properties that we are learning here. And you will recall that the physical properties that we are learning in our syllabus for organic chemistry, it's the boiling point, it is the melting point, and it is also the vapor pressure. Altogether, it is three of those physical properties, and you must know their definition. And in this instance, we can see that we've been asked to define the term boiling point. And from our examination guidelines, we know that the boiling point is the temperature. It is the temperature. And which temperature are we referring to? It is the temperature at which the vapor pressure it is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. It is the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Now, my dear learners, the first thing is for you to note that it is the boiling point, and boiling point refers to temperature. That is why we say it is the temperature. It is a given value. That is why it says boiling point, right? It doesn't say boiling. It's not a process. It's boiling point. So it is the temperature. And then which temperature is that? The temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. In other words, that temperature, when the pressure that is caused by the vapor is equal to the pressure on the outside, meaning the external pressure, which is the atmospheric pressure. When these two pressures are equal, then at that particular temperature that we will be measuring, we will say that is the boiling point. And all these keywords that I have underlined, my dear learners, they must be there, and they must be in the correct context, and they must be giving a scientific meaning of the term boiling point. So this is essentially what you need to know. My dear learners, I have told you once more that we are moving into the direction where a substance itself, rather a definition is given 2 marks or 0. So it's not always going to be an issue of part marking. It's most probably a 2 or 0. So if anything is missed there and it is not in the correct context, then you are going to lose marks. Altogether, you are definitely going to lose marks. So make sure that you get all the marks too. We don't really accept definitions that are partly correct. So take heed of that. Right. Then they tell us the boiling points of compound Q, R, and S are compared. So they are going to compare the boiling point of Q, R, and S altogether. And when they compare them, they then ask us in 3.2, give a reason why this is a fair comparison. So we need to check, why is it fair that the boiling point of Q, R, and S can actually be compared? Are we together? Now, to compare the boiling points of substances, the comparison must definitely be a fair one. And this one is fair because all the molecules that I am comparing, they are belonging to the same homologous series, which is alkanes. As a result, I can actually try and find out why perhaps the boiling point of hexane is bigger than or is higher than the boiling point of 3-methylpentane and even more higher than that of 2,2-dimethylbutane. So the molecules are different and they belong to the same homologous series, and therefore it is a fair comparison by the fact that they belong to the same homologous series. And it's an easy question there, and we allocate 1 mark. So the answer, it will be because it is because Q, R, and S belong. Q, R, and S belong to the same homologous series. So they belong to the same homologous series, which is alkanes. Right, they belong to the same homologous series, which is alkanes. Are we together? So that is why we can actually make this a fair comparison. Now, another learner could actually say, but if they belong to the same homologous series, what is it that we can look at that really tells us that this could be a fair comparison? Perhaps if these organic molecules have the same molecular mass. And what would make them have the same molecular mass is if they have the same molecular formula. Now, let us look at this molecule. If you look at this molecule, we can see its hex. In other words, the number of carbon atoms in this molecule will be 6. Then I look at 3-methylpentane. In 3-methylpentane, the meth part tells me that I have 1 carbon there. The pent part is telling me that I have 5 carbons. In other words, my dear learners, here I have 6 carbons as well. Then I look at Q, it's dimethyl. In other words, I have 2 methyl substituent, and 1 methyl is 1 carbon. So if I have 2 of those, it means I have 2 carbons. Then bute tells me that I have 4 carbons in that parent chain. So in total, I have 6 carbons. Now, if S has 6 carbons, R has 6 carbons, Q has 6 carbons, and they are all alkanes, and they are all described by the same general formula, most definitely, my dear learners, they are going to have the same number of hydrogen atoms. So remember, the general formula of alkanes, it's CnH2n plus 2. In other words, if I have 6 carbons, we know the N stands for the number of carbons, so it will be C6H2 into 2 plus 2. So the molecular formula will then work out to be C6, 2N. Remember, N is the number of carbons, so this will be 2 multiplied by 6. So it will be H, 2 times 6, it's 12 plus 2, it will be 14. In other words, the molecular formula of all these compounds, it will be C6H14. The molecular formula of 3-methylpentane, it's also going to be C6H14. The molecular formula of hexane is also going to be C6H14. So my dear learners, basically we can see that what we are comparing are organic molecules that have the same molecular formula. So they are all C6H14. So this makes for a fair comparison. Why? The answer there would then be, which is an alternative answer, it is a fair comparison because Q, R, and S have the same molecular formula and therefore the same molecular mass. And that's exactly how you write it. Q, R, and S have the same molecular formula and therefore the same molecular mass. If you don't say anything about the molecular mass, then we can give you a mark. And we definitely expect that the molecular formula will be the same. Why? Because the molecular mass, the molecular mass will be the same because the molecular formula is also the same. Are we together? So take note of that. Now, another learner could then realize that these molecules actually have the same molecular formula. So if they have the same molecular formula, what is happening to their structural formula? And they definitely have different names, right? This one is 2,2 dimethylbutane. This one is 3-methylpentane. This one is hexane. Now, when you see that the names are different, it means the structural formula is also going to be different. So Q, R, and S, they are organic molecules with the same molecular formula, but they will have a different structural formula. And you know that the structural formula will be different because the names are different. Now, if I then had to ask you, you would then say these molecules are isomers, or they are structural isomers. Now, if I ask you further and I say, what type of isomers are these? Elena is going to say to me, Menier, these are chain isomers. These are chain isomers. And why do we say these are chain isomers? Because when we define chain isomers, we say they are organic molecules with the same molecular formula, but a different type of chain. So the molecular formulas are the same here in Q, R, and S. So is the type of chain different? And the answer is yes. Why are we saying the type of chain is different? Because when you look at molecule S, which is hexane, hexane tells me that the parent chain here has 6 carbons. And I can see that there are no substituent. There is nothing that comes before the parent chain. When I look at molecule R, which is 3-methyl pentane, I can definitely see that the parent chain, it's pentane, it's 5 carbons long. And I have a methyl substituent. Remember, the methyl substituent is going to attach to the parent chain. So it is a branch. Altogether, it is a branch. So it means if I look at S and R and I compare them, I'm going to say S is a straight chain alkane because I don't have branches, I don't have substituents. When I look at molecule R, I'm going to say molecule R is a branched chain because I have a methyl branch there, I have a methyl substituent. When I look at 2,2 dimethyl butane, I am then going to say I have substituents and it's 2 of those because it's a dimethyl. I have 1 methyl on carbon 2. Again on carbon 2, I have another methyl. So on Q, it means I have more branches. So when I compare R and Q, I can actually say R is less branched because it has 1 methyl branch. But I will say Q is more branched because it has 2 methyl branches. So comparing Q, R, and S, my dear learners, I can see that S is a straight chain alkane, R is a less branched chain alkane, and Q is a more branched chain alkane. Altogether, my dear learners. So the chains are different. Another one is straight, the other one is less branched chain, and the other one is more branched. And that is why we say it has different types of chains. And we can actually classify these Q, R, and S as chain isomers altogether. So another learner could have said, this is a fair comparison because Q, R, and S are chain isomers altogether. So please remember that, my dear learners. Right, so that is another possible answer that you could have given. Also, my dear learners, what you could have said is, by just looking at this molecular formula, can you see that the number of carbon atoms is the same and the number of hydrogen atoms is the same? So it is still a fair comparison because of that, because they have the same number of carbon atoms as well as hydrogen atoms. So that is another reason why this is a fair comparison. So take note of that. When a question is given perhaps differently, you must know how we look at a comparison being fair. Right. We continue with question number 3. They say to us, the boiling points of Q, R, and S are given below. So there we can see them, they are given, and they are not necessarily in the correct order. So it means the order there is not an order of Q, R, and S. Maybe it is, maybe it isn't. That is why they are saying not necessarily in the correct order. Now, the question says, okay, we can see one of the boiling points is 55 degrees Celsius. For R, it's 49.7 degrees Celsius. No, the first boiling point given there is 55 degrees Celsius. And we don't know for which compound. For the other one is 49.7 degrees Celsius. We don't know which one is that. And the other one is 68 degrees Celsius. So in our heads, we most probably are going to have to check which of these is Q, which of these is R, and which of these is S. So that is very important. Now the question follows. Which one of the 3 boiling points is most likely the boiling point of compound R? Explain the answer. So there are 2 parts to this question. The first one is we are going to have to identify the boiling point of compound R and explain why we say that is the boiling point of compound R. Now, when you check there, my dear learners, you were able to see that we are looking at molecules that belong to the same homologous series, right? They were all alkanes. Right. Now, my dear learners, if molecules belong to the same homologous series and the boiling points are different, right? We can see they are different for Q, R, and S. We need to ask ourselves why these molecules have different boiling points. And when you look at Q, or let me start there. When you look at S, they told us that the name of S is hexane, and the name of Q, we will remember that it's 2,2 dimethylbutane. And then R, you will recall that the name of R is 3-methylpentane. Now, what can we see about these molecules? You can definitely see that the parent chains are not the same. You see there, the parent chain is a hex. It has 6 carbons. The parent chain there, it's a pent. It has 5 carbons. The parent chain there, it's a bute. It has 4 carbons. And this, my dear learners, is the reason why the boiling points of Q, R, and S are different, because the chain length is different. Can you see the chain length there has 6 carbons in the parent chain? The chain length there is 5 carbons in the parent chain. The chain length there is 4 carbons in the parent chain. In other words, hexane is a molecule with a longer chain length. Pentane, rather 3-methylpentane, is a molecule with a chain length that is smaller than that of hexane, but larger than that of 2,2 dimethylbutane. And then butane, it has 4 carbons in the parent chain, so it is the one with the shortest chain length in terms of the parent chain. So you must know that the longer the chain length, which is determined by the parent chain, the longer the chain length, the higher the boiling point. So we can see that definitely in this parent chain, the higher the boiling point. So we can see that the parent chains don't have the same chain length, and that is why the boiling points are going to be different altogether. So the longer the chain length, the higher the boiling point. But remember, when you look at the chain length, you must actually focus on the parent chain and see how long the parent chain is. Now, hexane is the one with the longest parent chain length, right? Is the one with the longest chain length, so it must be the one with the highest boiling point. And the highest boiling point here, it's 68 degrees Celsius, so it means this is S. When I look at Q, Q is the one with the shortest chain length altogether, which is a butte, because these ones are part of the branches, the substituent. So it's a butte. So it has the shortest chain length, so it must have the lowest boiling point. And the lowest boiling point is 49.7, and that will be Q. And when you look at R, R has a boiling point, rather, it has a chain length that is greater than that of Q. In other words, the boiling point of R must be greater than the boiling point of Q. But further on, my dear learners, when you look at R, it has a shorter chain length compared to S. And this then tells me that R must have a boiling point that is lower than that of hexane, but greater than that of 2,2 dimethyl butane. And definitely the answer there is going to be R. And actually, it became quite obvious as we were dealing with the boiling point of Q and S. So our answer there is, for the first mark, going to be 55 degrees Celsius with units. If you just write 55, we don't give you a mark because we don't know what 55 means. Then we then need to explain the answer. Now, to explain the answer here, my dear learners, we actually have done part of the work here. Now, I'm going to teach you something here. When you want to explain why the boiling point of one molecule is different from the other, or how you determine the boiling point, you must use 3 headings. And this is a recipe for you. You must talk about the cause. You must talk about the strength of intermolecular forces. You must talk about the cause. You must talk about the strength of intermolecular forces. And furthermore, you must talk about the energy needed to overcome the intermolecular forces. So these 3 headings, you must definitely use them, and they are going to help you a great deal. So in the interest of time, I will then call this heading 1, the cause. The strength of intermolecular forces, it will be heading 2, and the energy needed to overcome the intermolecular forces is going to be heading 3. Right, now under each heading, I'm going to put a bullet and I'm going to give my point for a mark. And these bullets, we mark them independently. The other bullet does not depend on the other one. The cause does not depend on the strength of intermolecular forces or the energy. So we will mark them independently. And hence, even if you don't know the cause, but you know the others, then continue with your answering. Right. So let us look at the answer. Now, my dear learners, it is definitely clear that because they belong to the same homologous series, the cause, you have to talk about the chain length. Honestly, at all material times, if you look at molecules that belong to the same homologous series and you determine that the boiling points are different, it will always be the fact that the chain length is not the same altogether. Right. So we can see that the boiling point of R is actually between that of Q and S. In other words, I must do, to explain the answer, I have to talk about R relative to Q and relative to S. So I can't talk about R relative to Q only. I can't talk about R relative to S only. I have to talk about R in relation to Q and S, because that is why R has a boiling point that is between Q and S. So that is the point of departure when you are going to answer this question. To say, but the boiling point of R is between that of Q and S. So I need to compare R in terms of Q and S. And that is how marks are going to be allocated. Now, let's start. I said we'll start with the first heading, and the first heading is the cause, right? I said if the molecules belong to the same homologous series, the cause is going to be the chain length. Because we are in the same homologous series, it means we differ by the chain. And the chain that is different is the length of the parent chain. So what can I say about R? Remember, R is 3-methylpentane, 5 carbons in the parent chain. For S, 6 carbons in the parent chain. For Q, 4 carbons in the parent chain. So I'm going to say R has a longer chain length, right? Because it has 5 carbons in the parent chain. It has a longer chain length than Q. That is true because R has 5 carbons in the parent chain and Q has 4 carbons in the parent chain. So it means R has a longer chain length than Q. But remember what I said. I have to give it in relation to Q and S. But R has a shorter chain length than S. Right, so R has a shorter a longer chain length than Q. But when I look at R again, I can see that it has a shorter chain length than S, because R has 5 carbons in the parent chain and S has 6 carbons in the parent chain. For that, my dear learners, you're going to get a mark, because I said to you, if they belong to the same homologous series, then the length of the parent chain is going to be different. That is the first heading, heading number 1. Now we go to heading number 2, where we are going to talk about the strength of intermolecular forces. So I'm going to look at the strength of the intermolecular forces of R compared to Q, and also of R compared to S. Right, we start. Now, if R has a longer chain length than Q, you will then remember I said to you, the longer the chain length, the stronger the intermolecular forces. And this is where I'm going to say the intermolecular forces, of R are stronger than the intermolecular forces of Q. Yes, definitely the intermolecular forces of R are stronger than the intermolecular forces of Q. How do we know that? Because we have seen in that question that R has a longer chain length than Q. And I have told you that the longer the chain length, the stronger the intermolecular forces. But remember, my dear learners, that we have to give it a relationship with both Q and S. And therefore, the intermolecular forces of R are stronger than the intermolecular forces of Q, but and you can see, my dear learners, I'm not lazy to write this. You definitely have to write it. But the intermolecular forces of R are weaker than the intermolecular forces of S. Why are we saying that, my dear learners? Because R, when I compare it to S, R has a shorter chain length. Compared to S. In other words, the intermolecular forces of R are going to be weaker than the intermolecular forces of S. And that is going to give me another mark. And the last mark there is when you talk about the energy, right? Now, this is what you need to remember. if the intermolecular forces are strong, right? If the intermolecular forces are strong, then, my dear learners, to overcome those intermolecular forces, you definitely are going to require a lot of energy. If the intermolecular forces are weak, then you will require less energy, a low amount of energy to overcome those intermolecular forces. Are we together? So that is essentially the case here, my dear learners. To then know that the strength of intermolecular forces determines the amount of energy that is needed to overcome those intermolecular forces. Right. And another word that we use is to say break the intermolecular forces. We are actually breaking them, or more accurately, we are overcoming them. Then this is where you are going to say, because the intermolecular forces there of R are stronger than the intermolecular forces of Q, I will then say more energy is needed, more energy is needed to overcome the intermolecular forces. More energy is needed to overcome the intermolecular forces. More energy is needed to overcome the intermolecular forces of R than S, rather than Q, because those of R, the intermolecular forces, are strong compared to Q, so more energy is needed to overcome the intermolecular forces of R as compared to what? To Q. That is why I'm saying than Q, but less energy is needed to overcome less energy is needed to overcome the intermolecular forces of R than S. Remember, this statement, the last statement, is true because now the intermolecular forces of R are weaker as compared to the intermolecular forces of S. And hence, I will need less energy to overcome the intermolecular forces of R and as compared to S, because for S, I will need more energy to overcome the intermolecular forces than R. And these 3 points give you a correct explanation of why the boiling point of compound R is actually greater than that of Q, but actually less than that of S. So it is in between those. So remember, you must talk about the cause, the strength of intermolecular forces, and the energy. And for this one, you definitely had to compare R with both Q and S in order for you to get all your marks. So that was very critical. So check the question, use the correct context. Now, What are you not allowed to talk about here? You are not allowed to talk about a bond altogether. We are not talking about bonds here. We are talking about intermolecular forces altogether. Intermolecular forces. So when you are actually talking about bonds, we are talking about something else, which is not intermolecular forces. So we have seen in most instances, learners saying more energy is needed to overcome the bonds of R. We are not overcoming the bonds. We are overcoming the intermolecular forces. So very critical. And I still want to remind you, if we want to know why the boiling point of this compound is different from the other one, use 3 headings. And again, the first heading, which is the cause, you must check first if you are dealing with the same homologous series or not. If you can see that you are dealing with the same homologous series, it means those molecules have a different boiling point because the chain length is different altogether. Right, so that is how you would have got your 4 marks. 3 marks here, and the first mark was that one of the boiling point, which was 55 degrees Celsius. Right, I hope you are happy with that one, because I am. We move to the next question. Which is 3.4, and it's part of the same question. They say to us, a mixture of equal amount of P and T, right? The same organic molecules that were given on the table is placed in a flask and heated to a temperature below their boiling points. Assume that no reaction or condensation takes place. The vapor produced is collected in a syringe. So here we have P and T, my dear learners, and from this P and T, they were put into a flask, and it is a mixture, as you can see there, it's a mixture of P and T, and they are in the same flask, and they are then heated to a temperature that is below their boiling points. And assume that there is no reaction that is taking place between P and T, and there is no condensation that is taking place. In other words, water is actually not being released. Then they tell us the vapor pressure produced. So there will be vapor that is produced, is collected in a syringe. Now, the questions follow. Which compound, P or T, will be present in a greater amount in the syringe? Right. You must then go back and check, out of these compounds P and T, which one is P and which one is T? We can see that P is pentanal. We can see that T is pentan 1-ol. Right. We go back. We write down. We make notes so that we are able to remember. So P is definitely pentanal pentanal. T, it's pentan 1 all, right? Pentan 1 all, just to double check quickly. Yes, it's definitely pentan 1 all. Now, the one that is going to be in a greater amount in the syringe must be the one that is going to be in a greater amount in the syringe is the one that will have a vapor pressure that is high. Remember, it will have a greater amount of vapor, so the vapor pressure is going to be high. And we know the relationship again between vapor pressure and the boiling point. In other words, the one that is going to be in this syringe, remember now, this is the flask, right? And this is the syringe. So when you heat PNT, the vapor that forms will go through this delivery tube. This is called the delivery tube, and it will go into the syringe. So the substance that is going to be in a greater amount in this syringe will definitely have a higher vapor pressure. And if it will have a higher vapor pressure, it means it must be the substance with a boiling point that is low. How do we know that? Because we know that if the vapor pressure is high, then the boiling point is low. And it's true, the substance with a low boiling point will boil faster, right? As you are heating the substance, and more of that vapor is going to go into the syringe because the substance will boil quickly because it will be having a low boiling point. In other words, the vapor pressure will be high because it will be in the greatest amount in the syringe. So now, for me to be able to answer this question, I will need to first know which substance is going to have a low boiling point and which substance will have a high boiling point. And the one which will have a low boiling point will boil faster, will form vapor quickly, and it will form more vapor because the vapor pressure will be high, and that will be the substance that is in the greater amount in the syringe. Are we together? Right. Then we say, okay, here I have pentanal and I have pentan 1 all. Now, to compare maybe this in terms of boiling point, which one will have a low boiling point, which one will have a high boiling point, I then check. Can you see there, my dear learners? This is a pent. This is also a pent. So I am dealing with same number of carbon atoms, but you see this is pentanal. So this is an aldehyde. And this is pentan 1 all. And we know that pentan 1 all, the name ends with all, so this is an alcohol. Now, my dear learners, we know when we are dealing with aldehydes, right? Aldehydes, they have dipole forces. And I don't want to complicate this for you because they have dipole forces in addition to London forces. But we won't focus on that. We'll focus on those types of intermolecular forces that really have an effect on the boiling point. And the alcohol, we know the type of intermolecular forces that we get are hydrogen bonds. And perhaps I will write this for you as we go further altogether. And we know again, when we compare the strength of dipole-dipole with hydrogen bonds, we know hydrogen bonds are strong intermolecular forces. And dipole-dipole forces, they actually have what you can refer to as medium strength. In other words, hydrogen bonds are stronger intermolecular forces than dipole-dipole forces. Or another learner could say, dipole-dipole forces are weaker compared to hydrogen bonds. So we know, my dear learners, that if a molecule has strong intermolecular forces, which is pentan 1-ol, right, which is T, then I am definitely certain that because the intermolecular forces are strong, there will be more energy needed to break the intermolecular forces of pentan 1-ol. As a result, my dear learners, it then tells me that the boiling point is going to be high altogether. So the boiling point here is going to be high for T. Why? Because it has hydrogen bonds which are stronger and more energy will be needed to break those hydrogen bonds. And then we have pentanal, which has dipole-dipole forces, and it has weaker intermolecular forces compared to hydrogen bonds. So I will need less energy to overcome the intermolecular forces. And when I have less energy needed to break the intermolecular forces, it means the boiling point will be low. And therefore, because the boiling point of pentanal is low, then it means it will form more vapor and more quickly, and also a greater amount of vapor. So our answer to this question is definitely going to be P. And you can definitely see there, my dear learners, it's 2 marks, and what they're asking us, it's relatively easy, and that's what you should know. You must really have that confidence to say that, yeah, this time the question is really easy, and that is going to account for 2 marks. Then they ask us to explain the answer to question 3.4.1 by referring to the types and strengths of intermolecular forces. Right, so we have been given guidance there. We have to talk about the types of intermolecular forces and the strengths of intermolecular forces altogether. Now, my dear learners, here you should be able to see that these substances, P and T, are not the same. They are from different homologous series and they have different boiling points. And that is why they have different vapor pressures. And that is why P has a higher vapor pressure. It will have more vapor in the syringe. And now this, you can definitely see that it is determined by what? By the types of intermolecular forces. So my dear learners, please note, every time when you want to explain perhaps why the vapor pressures of 2 substances are different, or the boiling points of 2 substances are different, you will then check again the homologous series of those molecules. So I can see that for now I'm dealing with different homologous series. So if I'm dealing with different homologous series, my dear learners, you cannot talk about the chain length. You must talk about the types of intermolecular forces. Luckily for us here, they are guiding us. But if we didn't have that guidance as well, you must know that the boiling points of these molecules are different, or the vapor pressures of these molecules are different, and it is because they have different types of intermolecular forces, and this is because they belong to different homologous series. So you will talk about the types of intermolecular forces altogether. And we have to refer to that to explain why that one was in a greater amount. And this is because of the different boiling point and the different vapor pressures altogether. So I will go and I will start. I will then say, right, let's choose a different color. I will then say the first heading that Menier said I must talk about, which we mark independently, is the cause. I will then say, oh, the cause now has to be what? The types of intermolecular forces. I can't talk about the chain length. Remember, chain length, you only talk about it when you are comparing when you are comparing molecules of the same homologous series. So there I'm going to say, number one, the cause, pentanal, has, and we've already identified that, it has dipole forces and pentanol. Remember, pentanol is an alcohol. Pentanol. It's an alcohol, so it has hydrogen bonds. For this, my dear learners, for just identifying the types of intermolecular forces as per the guidance that they gave us, we will then have the first mark and there we'll have the second mark. And then number two, for the heading, remember I said we must talk about the strength of intermolecular forces. We must talk about the strength of intermolecular forces. Now, we already know that hydrogen bonds are stronger than the dipole forces. Then you will say hydrogen bonds of pentanal. Remember, pentanal, it's P. Pentanal, another learner could have said P, are, no. Hydrogen bonds of, sorry about that. There we go. Hydrogen bonds of pentanol are stronger than dipole They are stronger than dipole forces. They are stronger than dipole forces of pentanal altogether. So another learner here could have put it like this. If I just go back to number 1, because we already know from the table that pentanal it's P, another learner could have just said P has dipole forces and pentan1-ol, which is T. Another learner could have said, and T has hydrogen bonds. And then there you could have said hydrogen bonds of pentan1-ol, which is T, are stronger than the dipole forces of pentanal, which is P. And another learner, instead of saying hydrogen bonds, you could have just said intermolecular forces of pentan1-ol. We already know that those intermolecular forces are hydrogen bonds, are stronger than dipole forces, meaning they are stronger than the intermolecular forces of pentanal, because we already know that those intermolecular forces are dipole forces. Then, just to always be on the safe side, even if they said the cause and the strength, rather, the types of intermolecular force and the strength, you still know that you know this in terms of 3 headings, so there is nothing wrong. As long as the statement is correct, you could talk about the energy. Now, my dear learners, you know that the stronger the intermolecular forces, the more energy needed to break the intermolecular forces. So you will say more energy is needed to break the hydrogen bonds of pentan1-ol than pentanal. Altogether, my dear learners, and that will be, this one was the 3rd mark, and this one wouldn't be a mark simply because they said you need to talk about the types of intermolecular forces and the strength of intermolecular forces. But I always say, talk about everything that you know is correct and it is relevant, because this is 100% correct. So those are the tips that I can give you in answering these questions. Use these 3 headings. We are going to mark them independently. So even if the statement that you gave in heading 1 is incorrect, it will not affect the mark that you will get for the statement in number 2. If the statement in number 2 is definitely correct. So you don't lose hope, you continue, and you are definitely going to do well altogether. And we definitely know with the last statement, like I have said, pentan1-ol has hydrogen bonds which are strong. So if they are strong, that is why we say more energy will be needed to break the hydrogen bonds. Or another learner there, we said instead of using break, then you can use the term overcome, which is even more accurate, right? You could substitute that with overcome the hydrogen bonds of pentan1-ol than pentanal. And this is essentially how you'd answer this particular question. And it is relatively easy work. I really want you to collect all the marks that you can get in this particular topic altogether. And this is physical properties. It's a question from November 2020. 19, right, for physical sciences, right? We continue. Now we move to question number 4 of November 2019. And this question was on organic reactions. And again, we try another pen because we are very colorful. Let's try dark red. Right. Now, organic reactions as well, my dear learners, they will count for a lot of marks altogether. They will count for a lot of marks, plus minus 20 marks as well. It reads as follows. The flow diagram below shows how compound A can be used to prepare other organic compounds. So they are going to take compound A and they are going to use it to prepare other organic compounds. The numbers I, and IV represent different organic reactions. These are Roman numerals for 1, 2, 3, and 4. So there we've been given a flow diagram. It has organic reactions. And we are going to have to figure out what is definitely happening in this particular flow diagram. Are we together? Right. And really, my dear learners, when you look at a flow diagram, this is the first thing that I want you to know. Most of you don't get it right because you think this is everything that is reacting and this is everything that is forming. When we give you a flow diagram, it will always be incomplete. It means there will be things or substances that we omit, and that substance can be a reactant or it can be a product, and we want you to figure out the other reactant or the other product, or to determine the reactant or to determine the product. But we also omit conditions at times, and we want you to determine the condition altogether. So this question here, my dear learners, will have those omissions and you must figure it out. Because when you just look at it and you go from one compound to another, then you are going to have challenges in this regard altogether. Right, you will definitely have challenges in this regard because now you'd magically assume that a compound goes from X to Y altogether, magically. So always, my dear learners, figure out if there's any other reactant that is missing, or if there's any other product that is missing, or if there are any reaction conditions that you have omitted or that have been omitted in this particular instance. Right, there we have compound A, and there it is reacting with a base and it forms a primary alcohol. Now, my dear learners, we definitely know that a base, we use it when we are dealing with reactions, or let me just write it there for you. A base, we use it when we are dealing with reactions of haloalkanes. So immediately, my dear learners, when you see that we have been given a base that is part of the reaction, you must know this is reactions of haloalkanes. Let me just write it nicely there for you. Haloalkanes. And when it is reactions of haloalkanes, it means this haloalkane, my dear learners, is definitely a reactant. Remember, with reactions, my dear learners, we have reactants, we have conditions, and we also have products. So I definitely know that compound A belongs to the homologous series haloalkanes. Right. It belongs to the homologous series haloalkanes. Now, I can see that this was a haloalkane. So there was a halogen, meaning in this compound I have a bromine or I have a chlorine. And now it is reacting with this base. And all of a sudden, I am forming an alcohol. Now, if I'm going to form an alcohol, it means I'm moving from a haloalkane to an alcohol. I'm moving from a haloalkane to an alcohol. So now it means where I had maybe a chlorine atom or a bromine atom, we're not sure in this case, I now have an OH, which is a hydroxyl group. Then definitely it means where I had a halogen, it is now an OH, so it means I have performed substitution. Can you see we haven't even looked at the questions, but we are already learning here that this must have been substitution. Now, my dear learners, here we have correctly determined that I had a haloalkane. So somewhere on the carbon atoms that are there, there's either a chlorine or a bromine atom. And now I can see this was my reactant, this is now my product for reaction 1. In my product, can you see the halogen is not anywhere, there's no bromine or chlorine. It means it has been removed, right? And on top of being removed, wherever it was removed, my dear learners, it means something else was also removed there, which is a hydrogen. So either the halogen was there or it was there, or the hydrogen was there or it was there. But what I can see is that there is a halogen that was removed and a hydrogen. So when we have done that, it means we have elimination. The type of reaction that took place there must have been elimination because we have removed some substances. So it is definitely elimination. All together, my dear learners. Right, so this is essentially what you need to understand. And to make it simple, right, you will remember that haloalkanes are saturated. In other words, they have single bonds between carbon and carbon atoms. So now, can you see that to go from compound A to this compound, you are moving from a haloalkane which only has single bonds to a molecule that now has a double bond. So if you see that you are moving from single bond to a molecule that has a double bond, which means a molecule that is unsaturated, you must know, my dear learners, this is elimination. This is elimination. So if the reactant has single bonds and the product has a double bond, then you must know that you have done elimination altogether. So can you see we have simply identified what is happening there. Then here I have an alcohol, my dear learners. And this alcohol is reacting with this molecule here. And this molecule, I know it is a carboxylic acid because I see it with a COOH. And I said to you, my dear learners, this is a bit difficult to work with. So try and take this way of writing an organic compound, the condensed structural formula, into a structural formula. So actually this is C, this one, and it has 3 hydrogens. There they are, there it is, there it is. And then I have a C, and I can see that there it has an OH. Now I have 1, 2, so it means this other O must be a double bond O. So can you see this is definitely a carboxylic acid. It's a carboxylic acid because the functional group there is a carboxyl group. So this is a carboxyl group, only the functional group, but this is a carboxylic acid. So now, if I see that an alcohol in reaction 4 is reacting with a carboxylic acid, I know the product there, my dear learners, is definitely going to be an ester, because an ester is an organic molecule that is formed when an alcohol reacts with a carboxylic acid. And therefore, because this reaction 4 is an alcohol reacting with the carboxylic acid to form an ester, then the type of reaction there, which is 4, is going to be called esterification. This is then called esterification altogether, because it is forming an ester altogether, my dear learners. So remember that. Are we clear? Right. Then let us look at this reaction. Here I have this product or this substance, and this substance now reacts and it undergoes hydration altogether. It undergoes hydration. In other words, it is reacting with water, and water is HOH. It's H2O, but I prefer to write it like this altogether. And when this compound reacts with this one, it forms a particular product. And because we are going to add water, this is hydration, and because we are adding water. So the type of reaction that is taking place here is definitely going to be addition, because we are adding water, and we are going to form a compound that is called B, and that product is a major product. And because we'll be adding water, to determine the major product, we are going to apply the rule for addition, because we are adding water now. So we are performing addition. We are adding H2O. We are adding HOH. So we'll apply the rule for addition to see how the H and the OH is going to add. So this, my dear learners, it's already giving you answers. And when you get to the questions, it's easy. And this is how you should revise. And how do I know that this reaction 1 is definitely going to be elimination? Because when a haloalkane is reacting and you use a concentrated strong base, remember KOH is a strong base. You see it with, it's a metal K, and OH, which is hydroxide. It's a metal hydroxide. And this is definitely a strong base. So when you take a strong concentrated base and you put it into a particular haloalkane, then that haloalkane will undergo elimination. And it's not only this is not the only condition that must be met. You must also make sure that the heat is high, and you must also be using pure ethanol as a solvent. So let us answer the questions. The first question says, name the homologous series to which compound A belongs. So we have already established that it is a haloalkane. It belongs to a homologous series, haloalkanes. And that is going to give me 1 mark. The type of reaction represented by 1, 3, and 4. 1, we've talked, it's elimination. 3, it's substitution. 4, it's esterification. Right, we've already discussed that. So 1, it's elimination. 3, it's substitution. And 4, it's esterification. Esterification. And this is 1 mark for each. Altogether, 4 easy marks, my dear learners. Right? We go to the next question. They say, consider reaction 3. Write down 2 reaction conditions for this reaction. So under which conditions will reaction 3 take place? Right. There's reaction 3. Reaction 3 is when a haloalkane is undergoing substitution. So when a haloalkane undergoes substitution, then the conditions that must be met are as follows. Remember, I will just write this down for you. For haloalkanes, if you want haloalkanes to undergo substitution, and if you want them to undergo elimination, these are the conditions that you must remember. Elimination, and please take them down. For substitution, number 1, the heat must be mild. So you'll use mild heat. Now, if you just say heat, we won't give you a mark. The word mild must be there. But if you wanted it to undergo substitution, then no, if you wanted it to undergo elimination, then the heat must be high. So you will use high heat. Number 2, if you want it to undergo substitution, then you must use a dilute strong base. For example, NaOH, KOH, LiOH, any strong base. But in this case, it must be dilute. So if you just say dilute base, you won't get a mark because it must still be strong. If you say strong base, you won't get a mark because you must tell us it must be dilute. But if you want elimination, then you must use a concentrated strong base. Altogether. So it must still be a strong base. For example, your sodium hydroxide, your potassium hydroxide, any metal hydroxide. But it must be concentrated. So everything there must be there. 3, you must have more water in the solvent. More water in the solvent. So these are the three conditions. But when you want it to undergo elimination, you must use pure ethanol as a solvent. All together. So now, for reaction 3, we saw that it is undergoing substitution. So the conditions there, and they only wanted 2, you must say mild heat, definitely mild heat, dilute strong base, or more water in the solvent. Altogether. So any of the 2 is applicable in this case. And then they want the IUPAC name of the primary alcohol that is formed altogether. So we want to know what is the primary alcohol that is being formed. Right. Go back. Right. To get the primary alcohol that is being formed, one can actually say, but I don't know what compound A is. And if I don't know what compound A is, how will I know the structure of the primary alcohol? And this is why you must interpret this flow diagram. Can you see, based on reaction 1, I can see that compound A must have had how many carbons? 1, 2, 3 carbons. And therefore, if compound A had 3 carbons, it means this alcohol here must be an alcohol that has how many carbons? 3 carbons altogether. And I took heed of that because I could see that the product for reaction 1 had 3 carbons. It means compound A had 3 carbons. So now, the alcohol that they want here, firstly, it must have 3 carbons, and it must be primary. Now, if it is primary, it means, and let me just draw it for you first. Okay, firstly, I drew the 3 carbons, and because it's an alcohol, I know it must have the OH, and the rest of the molecule will have H's, such that each carbon atom has 4 bonds. And there each carbon atom has 4 bonds. Now, what are we saying in this case, my dear learners? We want a primary alcohol, and this is definitely a primary alcohol. Why is this a primary alcohol? They didn't ask us that, but will Somar talk about it? And we talked about it yesterday. Can you see the carbon that is carrying the OH? The carbon that is carrying the hydroxyl group is bonded to how many carbon atoms? It's bonded to only 1 carbon atom. Are we together? Right. So if it is bonded to only 1 carbon atom, then this is definitely a primary alcohol. So if we were asked a reason, for a reason why this is the primary alcohol, we would have said it is because the carbon which is carrying the OH group, which is bonded to that hydroxyl group, it's only bonded to which carbon? To 1 carbon. So it is a primary alcohol altogether. Right. Furthermore, my dear learners, the reason we have to start here, there is no way that you can give a name if you don't know the structure. So we were not asked for this altogether, but we had to work out the alcohol in order for us to be able to give it an IUPAC name. So to give an IUPAC name here, we'll say, okay, the number of carbon atoms here, it's 1. Okay, let me just do this. The number of carbon atoms here, it will be 1, 2, 3. Now, I numbered here from from right to left. Why? Because the hydroxyl group must be on the lowest numbered carbon. So to start giving a name here, I will say 3 carbons, it's prop. And remember, we don't just say prop, it's propan. And it's an alcohol, so the name will end with OL. And then remember, I need to give the position of the OH, and I can see it's on carbon 1. And that must go between the stem and what the name begins with and what the name ends with. And the other IUPAC rule is that I must have a hyphen between a letter and a number, a hyphen between a letter and a number. So this is propan 1-ol. So the first mark will be for propanol, and the next mark will be for giving the position of the functional group, making sure that there are hyphens between a letter and a number, and basically for the whole IUPAC name being correct. Are we together? Right. Then we go to question 4.4. We must draw the structural formula of compound B. Now, compound B, my dear learners, it was a reaction between, we'll just go back here, this primary alcohol, which is propan 1-ol, and this carboxylic acid. So it's a carboxylic acid with 2 carbons. So it was propanoic acid. Propanoic acid. So it was propanol, propan 1-ol, there's propan 1-ol, we've determined it, and it's reacting with this carboxylic acid, which is not propanoic acid, it's 2 carbons. Let's rectify that quickly. Right, 2 carbons, it must be ethanoic acid. Ethanoic, because eth means 2. Now, let me just give you some teaching here, my dear learners. You see, when this propan 1-ol reacts with ethanoic acid, you are going to form an ester. So they are basically looking for the structure of the ester. So in our learning for now, we are going to just write a balanced chemical equation to see how the ester forms. But that's not what they asked us. But from that balanced chemical equation, we will just extract the ester. So there we had propan 1-ol, which looks like this. We've already drawn it. And we saw that it is reacting with ethanoic acid. So ethanoic acid, on the first carbon, I will have a C double bond O with an OH. Remember, I said to you, is the oxygen that must bond to the carbon. So now my carbon 1 is actually on the left. And remember, esterification, it's a condensation reaction. Are we together? So water is released. Now, what I'm going to show you here, you don't show it if you were asked the balanced chemical equation, but it's just your rough work here. Is because when an alcohol, remember, this is propan 1-ol, and it is reacting with ethanoic acid. So it's a reaction between an alcohol and a carboxylic acid. I'm going to form an ester. And we know when we form an ester, during esterification, we have the release of water. There is condensation. So it means water is going to be one of the products. So we already know that. So we must have plus H2O. And you know, that H2O, you can just get it from taking an H there and taking an OH there and removing it. So that part gives you the H2O. And whatever you are left with after removing the H2O, you are just going to bond it together. And that will give you the structure of the ester, which is compound C. So you will be left with C, C, C. Right, I'm still on this side. So O, now I've removed this, so I'm going to join the O with that C double bond O. And then I continue to the right. And remember, every time around an oxygen, I must have 2 bonds, 1, 2. On this one, 1, 2. Altogether, then this molecule is correct. Each carbon has 4 bonds and each oxygen has 2 bonds. And this is the ester. And I have a code when I'm dealing with organic chemistry, which is RCP, to say when you deal with organic chemistry, we must have reactants, we must have conditions, and we must have products. And the conditions here are that you must have heat and you must have sulfuric acid. So if they asked us for a balanced chemical equation for reaction number, for that reaction between propan 1-ol and ethanoic acid, this would be the complete reaction. So my dear learners, here we were not asked for this, we were just asked for the compound which will form, which is the ester, which is this one. Remember, there are 2 products, it's this ester and this one altogether. But this one is organic and this other compound is inorganic. So they wanted the structural formula of the organic product. So we are dealing with this one. And this is the ester. And if you had to give a name to this ester, you would have said this part of the alcohol, you will change it from propan 1-ol, you will then change it to propyl. And this part of the ethanoic acid, you will change it to ethanoate. So the name of the carboxylic of the ester is then propyl ethanoate. So we'll start with the alcohol part, you will change it to something that ends with YL, so it's prop, so it's propyl. Ethanoic acid, ethanoate. And you don't say propyl ethanoate acid. It's as if you are still talking about the carboxylic acid. But they didn't ask for this. If you do this, my dear learners, you won't get any mark. We will mark the first structure that we see. So I was doing this just to show you how you form it. So the only answer they wanted there is that structural formula of the organic compound, which is your ester. Right. Yes, it was actually compound B. Okay. Now, my dear learners, actually what I drew for you here is compound C altogether, but I'm happy with that. We know how to deal with compound C, but really the question was on this one. They wanted compound B. They wanted compound B. So compound B is the reaction between prop 1 in and it's undergoing hydration, so it was reacting with water. Prop 1 in with water, right? This one was for reaction 4, and that's compound C. So let us deal with compound B. We saw that is prop 1 in, and they gave us the structure. Right. And they told us that it is undergoing hydration. In other words, it's reacting with HOH. This is water, and this is preferably how I would write it so that I know how to perform my addition. And remember, we've identified that it is addition, so the double bond is going to break, because I can't just add water there. I can't add H there and OH there, or OH there and H there without breaking the double bond. I have to break it. Otherwise, carbon will have 5 bonds. And we know if I'm going to deal with hydration altogether, then I'm going to need to heat this particular substance, and I will need sulfuric acid as a catalyst. Now, because it's addition, we definitely know that the double bond must break. So let us just break the double bond quickly. 1, 2, 3. So the double bond there has broken. The H is still there. 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 And the H is still there, but the double bond has been broken. So this molecule is not correct, because this carbon has 1, 2, 3 bonds. This one has 1, 2, 3 bonds. So it means I can add something there. I can add something there to make the 4th bond. I can add something there to add the 4th bond. And this is where in one carbon I will add the H, in another carbon I will add the OH. But now you realize that if I add the H there and I add the OH there, then this molecule will be propan 2-ol. But another person could say, what if I add the OH there and I add the H there? Then this molecule will be propan 1-ol. Remember, this is compound B. So now there are 2 possibilities. The H could go on the first carbon, the OH on the second carbon, or the OH on the first carbon, the H on the second carbon. So we then have to check that in this dilemma, what should we do? We don't choose for ourselves. And because we are adding, meaning we start from having a double bond to not having a double bond, then we must apply the rule for addition. And remember, the rule for addition, it's actually the opposite of the rule for elimination that we dealt with yesterday. The rule for addition, I want to put it simple to you. You just say H2 more. And you will remember the rule for elimination said H from less. From because you are removing and less. Here we are adding H2 more. So it is the opposite. This is actually what we call Markov-Nikov's rule. We call this one Markov-Nikov's rule. It is called the rule for addition. And if it says H2 more, it means where I broke the double bond, it's only these two carbons where I can add. So I need to add this hydrogen to the carbon that already has more hydrogens. And between these two, it's this one. So it means the H must go there, and obviously the OH must go there. And this will be the structure because we have applied the rule for addition. H2 more. And the IUPAC name, if they asked us, I would have said this is propan for 3 carbons, 2 because the OH is on carbon number 2, all. Propan hyphen 2 hyphen all. Right, so that answers that question there where we had to draw the structural formula for compound B, and then consider reaction 4, write down the structural formula of organic compound C and the name or formula of the catalyst that is used. So we just go back here and we say, okay, reaction 4, it's this one where propan 1 all was reacting with ethanoic acid. So the structural formula of compound C, we drew it there. It was the ester altogether. And the catalyst that is needed is definitely sulfuric acid altogether. And that is all I had for you for today. Now, I just want to give you a couple of tips there, is to say, under nomenclature, it's plus minus 20 marks. Under physical properties, it's plus minus 20 marks. Under organic reactions, it's plus minus 20 marks altogether, my dear learners. So please be able to work with organic chemistry because it goes between 48 and 60 marks. Most of the questions that we have done, we use them and to actually give you tips so that you actually do well in this particular topic. So that answers question 3 and 4 of November 2019, and yesterday we did question 2 altogether. So we will be continuing, but I want to start with topics where you can get easy marks. So tomorrow we will be talking to fertilizers, and perhaps based on time, we will then look at electrochemistry. Thank you so much for tuning in. Please send more questions to stemdigitalschool@africateamgeeks.co.za, and I can answer more of your questions tomorrow when you join me again between 7 and 9 o'clock. Thank you so much for tuning in and enjoy the rest of the evening. Goodbye.